it's negative 150. And then plus, all right, how much work was done? It says 60 joules of work is done on a gas. So that's work done on the gas. That means it's a positive contribution to the internal energy. That's energy you're adding to the gas. So 60 joules has to be positive. And so this is plus, the work done is positive 60 joules. Now we can figure it out. The change in internal energy would be negative 90 joules. But why do we care? Why do we care about the change in internal energy of the gas? Well, here's something important. Whether it's a monatomic or diatomic or triatomic molecule, the internal energy of the gas is always proportional to the temperature. This means if the temperature goes up, the internal energy goes up. And it also means if the internal energy goes up, the temperature goes up. So one thing we can say, just going over here, looking at the change in internal energy was negative. This means the internal energy went down by 90 joules. Overall, when all was said and done, this gas lost 90 joules of internal energy. That means the temperature went down. That means this gas is going to be cooler when you end this process compared to when it started. Even though you added 60 joules of work energy, it lost 150 joules of heat energy. That's a net loss. The temperature is going to go down. So this is an important key fact. Whatever the internal energy does, that's what the temperature does, and it makes sense. Since we know that an increase in internal energy means an increase in translational kinetic energy, rotational kinetic energy, vibrational energy, that temperature is also a measure of that internal energy. Note that we cannot say exactly how low the temperature went. This is a loss of 90 joules, but this doesn't mean a loss of 90 degrees. These are proportional, they're not equal. If I go down 90 joules, that doesn't mean I go down 90 degrees. I would have to know more about the makeup of this gas in order to do that. But the internal energy and the temperature are proportional. Let's try another one. Let's say a gas started with 200 joules of internal energy, and while you add 180 joules of heat to the gas does 70 joules of work. What is the final internal energy of the gas? Alright, so the change in internal energy equals Q, let's see, gas starts with 200 joules of internal energy, that's not heat. While you add 180 joules of heat, here we go, 180 joules, should it be positive or negative? It's going to be positive, you're adding heat to that system. So positive 180 joules of heat are added, plus the amount of work done on the gas. It says the gas does 70 joules of work. So most people would just do, alright, 70 joules. There we go. But this is wrong. This is wrong because this is how much work the gas does. This W up here with the plus sign represents how much work was done on the gas. If the gas does 70 joules of work, negative 70 joules of work were done on the gas. You have to be really careful about that. So we can find the change in internal energy. In this case, it's going to equal positive 110 joules. But that's not our answer. The question is asking us for the final internal energy of the gas. This is not the final internal energy of the gas. This is the amount by which the internal energy changed. So we know the internal energy went up because this is positive, and this is the change in internal energy. Internal energy went up by 110 joules. That means temperature is also going to go up. So what's the final internal energy of the gas? Well, if the internal energy goes up by 110 joules, and the gas started with 200 joules, we know the final internal energy, U final, is just going to be 200 plus 110 is 310. Or if you want to be more careful about it, you can write this out. Delta U, we can call U final minus U initial. That's what delta U stands for. U final is what we want to find, minus U initial is 200, so positive 200 joules was what the gas started with, equals, that's the change, and that's what we found, 110 joules. Now you solve this for U final, you would add 200 to both sides, and again you would get 310 joules as the final internal energy of the gas. Let's look at one more. Let's say you got this one on a test, and it said that 40 joules of work are done on a gas, and the internal energy goes down by 150 joules. What was the value of the heat added to the gas? Note, we're not solving for the internal energy this time, or the change in internal energy. We're trying to solve for the heat. What's heat? Heat is Q. So this time we're going to plug in for the other two and solve for Q. What do we know? 40 joules of work are done on a gas. So this work has got to be a positive 40 because the work is done on the gas and not by the gas. And we know the internal energy goes down by 150 joules. It means the change in internal energy has to be negative 150. So if I plug in here, my delta U, since my internal energy went down by 150, delta U is going to be negative 150. Q, we don't know. So I'm just going to put a variable in there. Q, I don't know. I'm just going to put a Q in there. I'm going to name my ignorance and I'm going to solve for it. Plus the work done. We know the work done was 40 joules and it's positive 40. Positive 40 because work was done on the gas. Now we can solve for Q, the amount of heat. The value of the heat added to the gas is going to be, if I move my 40 over here, I subtract it from both sides, I'm going to get negative 190 joules. This means a lot of heat left. 190 joules of heat left the system in order for it to make the internal energy go down by 150 joules. And that makes sense. 40 joules of work were added, but we said the internal energy went down. That means the heat has to take away not only the 40 that you added, but also another 150 to make the energy go down overall, so the heat taken away has to be negative 190 joules. Alright, so those were a few examples of using the first law. Basically, got to be careful with your positive and negative signs. You got to remember what these things are, that Q is the heat, W is the work, delta U is the change in the internal energy, which, don't forget, that also gives you an idea of what happens to the temperature.
So I hope this presentation has shown you clear concept about work, heat and internal energy relationship. Now next example for first law of thermodynamics. Let me take a case of a gas confined in a cylinder with a movable piston. Here the piston is movable and this is insulated area, and here heat is added with this flame. So Q is added from here only. So this is a conductor. So what is the value of internal energy of the gas in the cylinder? Here the gas is there. It only depends on the temperature of the gas and not on its volume or its pressure. The internal energy is fully the function of temperature, and if the heat is added at constant volume, say here if the volume is remain constant and heat is continuously added, no work is done. Yes, the piston is, this is not allowed to move, so work is not done. So the heat is added equal to the increase in thermal energy. Here thermal energy will increase. The internal energy is a state function, that is, it is not dependent on the process. It only depends on the initial and final temperatures. So this is the equation. Delta E internal is equal to Q in. Q in is equal to CV dt, and hence dE is equal to CV dt, that is NCV into dt. Now say the example of free expansion. Here the gas is filled up in this chamber, here is the valve and this is the vacuum cup. Both the volumes are equal. Now if we open this valve, this gas will have the free expansion in this vacuum. So for a gas low density and ideal gas, a free expansion does not change the temperature of gas. The temperature will remain constant for an ideal gas for at low density. See, this is the case of the gas, confined gas in a cylinder with movable piston. Here the piston is movable, load is employed over here, so work is done if this is allowed to move and if heat is added from here. So heat transferred to the system. In this case, if heat is added at constant volume, as in the first case here, the volume is constant, no work is done. So the heat added equal to increase in thermal energy. So this process is the process at constant volume, and thermal energy of this gas will increase if this is not movable piston. So these are the two equations to find out value of heat transfer. dQ is equal to CV dt, that is NCV dt, or CV into delta T, that is change in temperature. In the second case, this case, if the heat is added at constant pressure, the energy transferred will be used to expand the substance and to increase the internal energy. If here the pressure is maintained at constant, so volume will increase and the piston will move. So in this case, at constant pressure, the change in volume will cause the work done W, and the equation for that work done is equal to Cp into delta T or Cp into dt. Now applying the first law of thermodynamics, in this case dE is equal to dQ plus dW on, so Cp dt minus Pdv, Pdv is equal to Cp minus Cv into dt, and this is the equation. If the substance expands, it does work on its surroundings, and the expansion is usually negligible for solids and liquids, so Cp is nearly equal to Cv for the solids and liquids. Now summary for this case, heat energy can be added to or lost from the system. The value of the heat energy transferred depends on the process. Typical processes are at constant volume and at constant pressure. For the case of ideal gas, Qv is equal to Cv into delta T or dQv is equal to Cv dt, and Qp, that is at a constant pressure, Cp into delta T or dQp is equal to Cp into dt. Cp minus Cv is equal to N into R, and for solids and liquids, as the expansion at constant pressure is usually negligible, Cp and Cv both are equal, and hence for ideal gas, from the kinetic theory, for monoatomic gases, Cv is equal to 3 by 2 N into R, and for biatomic gases, Cv is equal to 5 by 2 N into R. This is for ideal gas. Now the example for the first law, this is the application of work done on a system. W on is the energy transfer as work to the system. When this energy is added to the system, its value will be positive. So here piston is moving from here to here. The force is employed over here, which is equal to pressure into area, and by integration we can find out work done on the gas, and W on gas is equal to V1 to V2 Pdv, and W on gas is equal to minus W by the gas. On PV diagram it could be represented like this: P versus V. W on gas is equal to, for constant pressure, minus V1 to V2 Pdv, P into V1 minus V2. P0 V0 are the initial pressure and volume, and delta V, this is the change in volume, that is dV. If 5 liter of ideal gas at a pressure of 2 atmosphere is cooled so that it contracts at constant pressure until its volume is 3 liter, what is the work done on the gas? That is equal to 405.2 joule. That could be computed with this diagram and by putting the values in this equation. These are the PV diagrams for these 3 types of cases, where constant pressure, constant volume and constant temperature. In the first case, final position is PFVF and initial position is represented by PIVI. So connecting an initial state and a final state by 3 paths, from 1 to 2 we can go by 3 paths. One is this, constant volume and constant pressure. Second is constant pressure and constant volume, and third is constant temperature, that is also called as isothermal process. So for constant pressure, W on gas is equal to minus V1 to V2 Pdv, P into V1 minus V2, this one. For constant volume, W gas is equal to minus V1 to V2 Pdv, that is equal to 0, because for constant volume from here to here it is equal to 0. And constant temperature, integration of nRT upon V dV, so minus nRT ln V2 upon V1. So that is for this third case. So you can see here, in this case the work done is higher, here is lower, and here is moderate. So 1, 2 and 3 would be the order of work done in order, in increasing order. So let me conclude today's talk. So I hope you must have enjoyed today's presentation, in which we have make clear the relationship between heat Q, work done W, and change in internal energy delta U. We solved some examples and numericals, and we also discussed about the practical application of the first law of thermodynamics. We will continue next time with some more examples. Thanks to all.